need to stifle it. But no.
So, can you hear me without a mic?
Yes.
Yeah. Okay. So I will go very fast into what I will address in this talk. So I come from the astrophysical community, and as my research has been focused on the population of supermassive black holes, and the questions that people like me would like Lisa to answer are, well, some of them at least are listed here. How and when black holes form, how and when they accrete mass, how and when black holes merge, and how fast black holes spin. Not one black hole in the universe, the average black hole is a function of time from the Big Bang until now. And so I will try to address what Lisa can tell us about black holes in general. So one important point is the difference between what we know now and what Lisa can tell us. So this is the famous M-sigma relation with all the black holes in the local universe that have been measured, whose mass have been measured accurately. Most of these black holes have masses above 10%. What Lisa can observe is below this mass. Even if we look at black holes with masses measured through less secure methods, we see some black holes in the low mass range, but mostly Lisa will really see the black holes that we cannot see easily now. This is another example. This is the mass function of black holes, different methods for measurements. But so what I want to focus here, so here you can choose your favorite curve, green, red, or black. They rely on different assumptions on the population of black holes. You see here that more or less below the knee at 10 to the 7th solar mass, they kind of match. But at low masses, you can have up to 6 orders of magnitude uncertainties. And this is the range of masses where Lisa can inform us. And it's difficult to have this information from other techniques because low mass black holes are low luminosity GN, which are clearly more difficult to pick in flux-limited surveys. And low mass black holes have small spheres of influence. You have to trace the stars within these small spheres of influence, parsec scales below to measure masses. So that's why for the average astrophysicist, well, maybe not the average, for astrophysicists working on black hole evolution, Lisa is very important. One last point, all this clearly has to be a multi-messenger, multi-wavelength effort. We need to join the information that we get on black holes that are quiescent, and they're merging, and Lisa will pick up those through various types of observations. But we have to join this with information we get from electromagnetic radiation. For instance, the link between black holes and their hosts. So this is the type of background. So these are the questions that we ask, why we care about them, and what we hope will happen in the future that will get us to find these answers. So again, these are the questions. I will briefly, I promise, touch on some of those. With the goal of, okay, this is what we can model today. I'm not saying that the models I present represent the truth of the universe, but just an example. So we will look through this example and see what type of inferences we can make through different types of observations. So let's start with the basic assumptions. We say black holes merge in the universe. We will see thousands of mergers, well, not really thousands, but what does the merger rate that Lisa will detect depend on? Well, basically it will depend on how many black holes we have in the universe. So how and when black holes form. The masses that black holes have as a function of time will depend on how black holes grow in mass. So the accretion and merger history of black holes. You need these two pieces to understand the flow of information that Lisa will give us, But these are also, after the fact, the information that we want to have from our observations in the electromagnetic or gravitational wave band. So I'm very lucky. I come after Priya, who gave a great introduction. So I can go and skip the details. But so now let us think of, let's form black holes. I'm a black hole fairy, and they say there is a black hole here. What is this here? What is the mass of the black hole? And when is this here? Well, I will make things simple here. And I will just focus on two models of black hole formation that predict that black holes are either small or large. These are the first black holes that are born in the universe. I said, Priya has already given a great introduction. If the first black holes are the remnants of the first stars, so we just follow natural star evolution, just in a different context. First stars are massive, the first black holes are massive. You end up with a population of black hole seeds that are small, order of a few hundred solar masses at most. Then you can have large seeds. I'm not going into the physics of this, Priya has already discussed this, but you can have black hole formation models based on gas dynamical collapse or stellar dynamical collapse, dynamic instabilities mostly, that predict that black holes at birth are large, massive. And in this context, massive is about, more or less, about 10 to the 5 solar masses or so. So if you take this simple approach here, you have a model that has a lot of small seeds and a model that has lower number of large seeds. A simple way of putting this is to say, let's construct the mass function of the black hole seeds. This type of plot, the number of black holes is a function of mass, for the seeds, for the first black holes that are born, contains a lot of information. So you see here different models. So these are the Pau-3 stars, the small black holes. The mass function speaks at about 100 solar masses. Direct collapse seeds, as I said, this is probably the upper limit to black hole masses, speaks at about 10 to the 5 solar masses or so. And then you have intermediate models that I will not discuss in detail here. Benedetta De Vecchi, the author of this paper in the audience, you can ask her more details. Now, this plot, however, compresses some information. For instance, this doesn't take into account the time over which black holes form. So, for the purpose of this talk, I was asked to give a general review. I will mostly focus on the masses of black holes. You can repeat the same exercise with different information. For instance, the redshifts when black holes form, so the time after the Big Bang. So this is our starting point. However, what we measure is never this. What we measure is the convolution of birth with evolution. These black hole seeds probably were born a few million years after the Big Bang. What we observe is, well, now is 13 billion years. So you have to convolve the birth with evolution, with the cosmic evolution throughout time. So your initial conditions are up here. This is high redshift. But what we see today is here, down here. In the cosmic, in the currently favored models for galaxy formation, evolution, and function of time, the first galaxies were small at early times, and they became larger and larger through accretion and mergers. So we call this a merger tree, like a family tree for a family. The Milky Way had parents, grandparents, and so on. This is today, this is 13 billion years ago. These are galaxies, and these black dots are the black holes that grow inside galaxies. They have to follow the same sort of hierarchical evolution. So any information that we have to decode it to get the astrophysical information. What were the seeds and how they grew as a function of time. So if we start from small seeds, hundreds to about 100,000 of solar masses, then we grow through a sequence of mergers Black holes merge when their galaxies merge, and black holes accrete when they're fed gas. Now this is very important because all the black holes that we know today are known through this process. Well, all the black holes except for the 40 that we have measured through the magnetic process. During this phase, the active black holes are AGN. We can pick up the luminosity of the disks surrounding them. Now, an important point that I just made down here is that we know, so if you start with, say, in the universe there are only 10 black holes, they're all 100 solar masses. So if you merge all these black holes and you make a bigger black hole, 1,000 solar masses, you haven't changed the total mass density in black holes in a function of time. You have a limited amount of mass. When black holes accrete, they grow in mass through accretion of external matter. So overall here, the mass density in black holes will grow as a function of time. And it is good because we can use this as a constraint for our models. Because we make models, and then we want to make sure that whatever we use for our predictions makes sense, at least with current observations. So how do we typically model the mass evolution, the growth of black holes from seeds, hundreds of solar masses, 100,000 solar masses, to billions of solar masses? The black hole in the Milky Way is tiny, 10 to the 6 solar masses. The black hole in M87, CD galaxy and center of the Europa cluster, is more than 10 to the 9 solar masses. So you have to grow these black holes as a function of time. So clearly black hole mergers happen, or that's what we all believe in this room. And the dynamic evolution is important to understand, for instance, the merger rate. But we don't expect black hole mergers to be very important in the build-up of the mass, even of the most massive black holes that we know today. When we model the mass growth of black holes, from tiny seeds to today, this is dominated by accretion, the input from the external matter that comes close to black holes. And several times in this conference, about this workshop, has been said that it is not completely clear how it happens. But if you are a very simple person, like I am, you may have to take very simple assumptions. For instance, most of models that grow black holes as a function of time in these cosmological models assume that black holes grow in mass following mergers of galaxies. This is because of the destabilization of the gravitational potential that creates gas inflows. We typically expect that the growth of black holes gets the black holes up to a certain limit, which is typically expected to be about 1,000th of the mass of the host, the famous Hand-Signal relation and feedback relationships. So, on rule of thumb, the black hole, a galaxy is 1,000 times larger than its black hole, and we typically expect that it's on or below the Eddington limit simply because we don't observe many super Eddington quasars and AGN quasars. So you can make these very simple assumptions. See here, they're very, very simple. And we're lucky enough to be able to reproduce a large number of observational constraints, as Priya has shown this morning. So I'm not showing all this. So now you start from your seeds at high redshift. This is about a few million years, 100 million years after the Big Bang. Time flows this way. This is the mass of the black holes. You start from your seeds. That can be either the low mass, small Popper remnants, or the large seeds created by the collapse. They grow through this series of galaxy and black hole mergers as a function of time. Until in this case, for this particular case that I show here, they reach about 10 to the 9 solar masses. Now the interesting point that we wanted to make here is that basically most, if not black holes, enter the LISA band. LISA can observe black holes with masses between about 10 to the 4 to 10 to the 7 solar masses with high signal to noise ratio. So at some point, most black holes enter that band. So that's great. LISA can offer us a window on the high redshift universe and the early evolution of black holes. So what we can do through the so LISA will help us disentangle the formation and growth history of black holes as a function of time. On the other hand, now, 15 years before LISA flies, we can make simple assumptions on formation and growth and see what is the power that LISA has to discriminate between these models.
So, Marta, it's not a big effect, but
That's rest mass that you're showing.
Yes, yes, I'm very astrophysical minded. So yes, this helps at high redshift masses will be redshifted by redshift.
Sorry, what are the two curves in each plot?
Two different cases, just to show cosmic variance.
Ah, okay.
Okay, so you need that. So now if you want to create a toy model, on top of knowing the masses and the redshifts of the black hole, the masses of the black holes as a function of time, you need also to know how and when black holes merge, and how fast black hole spins. This is because, as Luciano showed this morning, the wave forms depend on spin also. Although luckily most of these non-spinning waveforms work. However, in half an hour I really don't have to talk about this, but Massimo Dotti has run the most lovely simulations on merging black holes and the evolution of their spins. So I will just ask you to trust me on this, that these are two other ingredients that go into our models. If you wanted coffee, I can show some of his results, or he can show them. Okay, so now we have these models in which black holes form, grow, merge, and well, a world was expected. What can Lisa tell us about these models? So can Lisa observe or listen to the evolution of black holes as a function of time? What is the power of discrimination for these models? As I said, my goal as an astrophysicist is to know, to have an answer or a possible answer to the questions that I asked at the beginning. In principle, Lisa can observe two different types of sources. MRIs, so extreme mass radiation spirals, and black hole mergers, massive black hole mergers. Now, these two sources probe different black holes. So the populations that they probe are different. MRIs probe all black holes, regardless pretty much of the dynamical states, throughout the mass function of black holes, but at a low redshift. Black holes in the last few billion years from here. So MRIs cannot help us learn about the first sits. On the other hand, we don't need merging supermassive black holes like this. So at low redshift, probably these are very important sources. Black hole mergers instead probe the subsample of the population that are merging. It's not a large number. We will see in a minute that merging black holes are not that many, but enough to be seen. But they can probe black holes up to high redshift. So I came as a due to a limited amount of time, and I will focus here mostly on black hole mergers. So how Lisa can observe black hole mergers and tell us about their evolution as a function of time. So this is an exercise that was done first by the Lisa Parameter Estimation Task Force, and then I will build up on that. So we just took 4 different models of black hole formation and evolution. We kept it simple. These 4 models differ in terms of initial masses. S models have low mass, are the remnants of Poplar star. S is for small. L models have large black hole masses that derive from direct collapse models. And then you also model differently accretion. I will not go into details, but here models characterized by the letter E have lower accretion. Models with the letter C have higher, faster accretion. So we compared these 4 models, SE, SC, LE, LC. You see the various permutations here. And we calculated, well, first, how many black hole mergers we expect for these models per year. How many of these black holes can actually be detected with high signal-to-noise ratio using Lisa's sensitivity. And you see here that we detect about a few tenths per year, regardless of model, 20 to 30. And then you can look at how many of these mergers are detected with very high spatial accuracy or enough accuracy to get good parameter estimation. So this is the baseline. Now, all these models observational constraints, like the loss function of quasars, the N-string relation today. So we're quite confident that these are not super optimistic numbers. So this is the first number that we were asked to calculate. How many black hole mergers would LISA consider? Now the next question is, with say 15 or 20 black hole mergers, can we say something about the black hole population, which is the initial question that I asked? So what can LISA tell us about the real black hole population? So this is the next step. Can we distinguish models based on the small number of black hole mergers that LISA can detect? And this is more recent work that I've done with Alberto, John, who are here to answer your questions on the statistical analysis and memory care. So in other words, can we infer the information about the black hole population from the event set that LISA observes? So what we do, we use and observe and create a distribution of events that we then search for with models to see which model, in principle, provides a better explanation of the data. So from the different models, we can see which type of formation and evolution model is good for this description. So we parameterize our models. We use the same four models we use for the LISA point estimation task force. And we can describe, we found that the population of black holes can be described with a trivariate distribution of the masses of the merging black holes, their mass ratios, and the ratio distribution, the distribution of the times when events happen. Let me just show you an example. This is the merger rate. This is normalized just so that everything fits in one plot as a function of the mass of the merging black holes is the most massive of the two. Here I compare the S models with the L models. This is a function of time. This is the earliest black holes, and then this is today. So here, this for instance is one of the distributions that we analyze. The distribution of the masses of merging black holes. And you see here that these two models differ at higher redshift, and they become much more similar today because we have to match the same observational constraints that we have from local black holes. Then we assume something about LISA, that you can observe systems only if their signal-to-noise ratio is above, say, 8 or 20. These are two typical numbers. We also assume different durations for the LISA mission from 3 months to 3 years. So we create data sets from our models, and then we search these data sets with our distributions. So given the data set D and 2 models, A, B, and I will describe the various models in a minute, we calculate the likelihood ratio for the 2 systems. So these, the data, A or B are 2 different models, and if we find a likelihood ratio of, say, 2, it is a logarithm, then this means that the probability of drawing the observed distribution D from dataset A is 100 times more probable than drawing it from the dataset B. Again, the 4 models that we use are the S models, small SIDS, large SIDS, with the 2 different efficiencies of accretion. So these are the 4 models that we compare, and we call a successful detection if the if the likelihood is characterized by the right model that describe the data set that we built. And we also have a false alarm rate if instead we're using the wrong model. So we can create these sort of curves where for different data sets we have the detection rate as a function of the false alarm probability. So if your detection rate is better than your false alarm probability, you are doing good. This is a good sign. If you have more false alarms that correct detections, then your technique is bad. LISA cannot distinguish from the data set that LISA gives you. You cannot distinguish different models. The
How
good
many
news.
detections typically for Clémence? How
Sorry?
many detections for Clémence? How many events are we talking about?
So if you have 20 events per year, it's about a third of that. Correct? Okay, so these are some curves. Okay, so this is for a signals noise threshold of 20, 3 months, LISA mission, 1 interproject. So this is a very pessimistic assumption. Here we compare different models. So for instance here, if we look at 1 to 2, it means, sorry, let me go back to one slide. Model 1 is small seeds with inefficient accretion. Model 2, for instance, is small seeds, more efficient accretion. So these models will not differ on the total number of black holes as a function of time. So the merger rate will be very similar. The masses of the merging black holes are different. So models 1 to 2, this red curve, represents two models that are very similar by construction. And still we're doing pretty well. So this means that observations of gravitational waves through LISA can really tell us something about the population of black holes that we observe. In other words, we can start answering the questions that I asked at the beginning. How many black holes are there? What are their masses? And how do they grow with time? So how many black holes are there? You have to compare, for instance, model 1 to 3. A model with many small black holes, or a lot of, not many small black holes, or a few big ones. These models are very different, so you will see a very high probability of detecting them. But you can even distinguish between two models that change really by how fast black holes grow as a function of time. Now, I talked about 10 black holes mergers per year, 6 in 3 months or something like that. Now, after Tamara's talk, you might wonder, well, but have we seen any binary black holes? Have we seen any binary gem? Well, in fact, one of my colleagues rushed to my office after the release of some analysis that done on the SDSS that found 1 or 2 or maybe 3 binary quasars out of 1,700 sources. So how does that small number reconcile with the tens of mergers per year that we detect? As I said, very often after he rushed in my office and asked this question, I thought, oh my gosh, everything is wrong. I have to resign very quickly. That was the first minute, and then I thought, okay, let's open my computer and calculate these numbers and see by how much I'm off. Now, I will take just 2 minutes, I promise, to show you some constraints that we get from the same models that we use to analyze the LISA population, so these tens of black hole mergers per year, but when we look at them in electromagnetic radiation. So I look at constraints on the number of binary quasars, and here I'm using Julian's suggestion to define binary systems. Those are actually a bound binary, sub-parsec or so separation, and dual or pairs of HM, so kiloparsec separation. Again, Tamara has described these systems. I will not go into details. Oh, by the way, I stole this slide from Monica, so I'm very grateful here. So we're looking here for systems like those that Tamara described, black holes that are in a bound binary with 1 or 2 circumbinary disks. So they are very close. Their orbital velocity we selected here 2,000 kilometers per second or higher. This is because this exercise was tuned on the Sloan SDSS quasar catalog. For each pair of black holes in my catalog of mergers, those that we analyzed for LISA, we assign luminosity based on some simple assumptions, and can go in details if there are questions. And we assign a lifetime to each binary. Here we assume that in these circumbinary disks, You can derive a lifetime based on the masses, mass ratios, and luminosity of the systems. This is work based on a work by Salt and Hyman with his Roberts. If you have a merger rate, a luminosity, and a catalog of quasars with a given flux limit and a volume, you can derive constraints on the number of binaries that you detect, or you expect to detect. These are just two flavors of the same model. What we predict is that the number of detectable binaries are not many. So about 0.1 or so per square degree, with the characteristics that are needed to be detected. Now here I report the area of these surveys. So you see here that in the Sloan survey, so now my catalog is complete because I simulate the whole sky at the same time. But so this is an upper limit binary, so we expect less than about a few in the Sloan catalog. So this means that the numbers that we have analyzed for LISA are not off from the number of binaries that we expect to see in the local universe.
Quickly. So on the figure, that's in the whole sky or the Sloan area?
This is all sky.
Okay.
This is per square degree.
Yes.
Oh, I didn't know.
So if this is per square degree, multiplied by the area of the Sloan.
But doesn't that multiply to give me like 5
Sorry,
Maybe
Sloan
my
was
math's wrong.
analyzed to ratio 0.7.
Oh, okay.
This is because you have to use oxygen lines that drop off ratio 2.
More like 5 to 10, right?
Yes, if the sample is complete, yes. I don't think, yes, these were the numbers. So I will not talk much about this, but we repeated the same exercise for dual systems, so separated, instead of being detected as by line shifts optically as binary system, dual systems here. Again, same catalog, different assumptions. I can go through the assumptions one by one if Matt was not standing there. This is preliminary work. In fact, I show you numbers, but there are no error bars. That tells that it's preliminary. Here I just cut in masses. I haven't applied any flux limit or anything. But so for the masses that you expect to see in the Sloan quasar catalog, about 10 to the 8 solar masses or so, again the numbers are pretty small. This is because of the lifetimes of these objects. They're short. And that's why, although they are there, we don't often see them. In other words, we are all happy about the numbers that we have analyzed for LISA. They're not too large, and they make sense with observational constraints. Okay, so these are the 3 questions that I'd like to have answers from. And I will just leave here my summary with what LISA can do for people asking those questions. Thank you.
Before I open it up for questions, the coffee's already out there, right, Ed? So it's getting cold. I just want you to think about that. Ask your question. At that point, I saw John's up, and then you, Neil. So John?
For the dual or AGN rate, I didn't really understand what you did. You assumed that the rate of having an AGN be active, a black hole be active in a merging galaxy is the same as it would be in a non-merging galaxy?
No.
It seems like a correlation there would be really important.
Yes. So let me go back here. So here I made some assumptions. So I assume that to see a dual system, well, you need a merging system. Mass ratios between 0.1 and 1. Below that mass ratio, things are not very stirred up. I assigned a merger timescale to each system based on simulations. This is all analytical work. It's very, very simple. We assume that it takes about 1 dynamical time between the time the merger starts and gas inflows into the black holes. So this is optimistic. We assume that both black holes light up at the same time. And they accrete for a given time that depends on how long it takes for them to reach the M sigma relation for the galaxy they're in. And from this you get the minimum time over which you can see both active at the same time. So this is the shortest description.
I just had a question about the graphs of n versus z there, the number per square degree.
This,
Is that like a cumulative? I
yes,
mean,
it's cumulative.
It's not a g and
No.
yeah. Okay, now I can understand it.
Yes.
Luciano and
This
then
is
we're
probably a
going to
silly
Tom.
question. Can you go back to the evolution of number of black holes as a function of redshift for the two scenarios?
This?
The other one, or the one where you had the two curves, thick and less one. Yeah. So, I mean, if I concentrate on the thin lines, they look very similar to me.
Yes. This is the same galaxy. So these are the two black holes with different masses put in the same galaxy. Let's let them evolve as a function of time. And what does it change? So here start with a smaller black hole. Here we start with a larger black hole, but the environment is the same. So the amount of gas that flows in to feed the black holes are the same. Is the same.
So but then,
So by construction, they have to be same.
but the question is then, can Lisa distinguish between the two lines?
I think, Luciano, what you're asking is, this line looks a lot like that
Yeah.
line?
Yes.
Yeah,
Yes.
okay.
Yes. What is distinguishable in which sense?
So you said that the difference between thick and thin is variance, okay?
Yes.
But then I see that there is a, within the variance, the thin blue and the thin red are.
But this is because, so for these two, I simulated the same galaxy. So thin and thick in each panel are two different galaxies. Thin and thin in each panel, in the two panels are the same galaxy, where just the black hole changes. So it's a different type of variance. I checked it before.
So I would guess that if you had lots and lots of galaxies, the ones that looked identical would wash out. As you can see, the thick ones are very different.
Yeah.
So it's just a matter of how many.
Yeah, exactly. Here I could put 100,000 curves, but they would not look the same, but in the same range pretty much. Just to give you an idea of the average growth.
Okay. No questions. Let's thank the speakers again.